Hello, I'm Franka Bause from the University of Vienna, and I'm going to talk about metric indexing for graph similarity search, which is a collaboration with David Blumenthal from the FAU Erlangen-Nürnberg, Erich Schubert from the TU Dortmund University, and Nils Kriege, also from the University of Vienna. So why do we want to search in graph databases? Well, basically everything can be represented as a graph, and in recent years we have more and more data that has to be processed, and a popular task has become to search for similar structures in large databases. For example, if we have a molecule, our task might be to find similar molecules because we assume that a similar structure implies a similar effect. And for searching, we can do two types of search. We can either do KNearest neighbor search, which is just searching for the k-nearest neighbors of an object, or we can do range search, where we search in a radius around the object. For both of those types of searches, a distance measurement is needed, and for graphs, we need a distance measurement that is suitable for graphs. A popular distance measurement that is very general is the graph edit distance, and it basically describes the cost to transform one graph into the other. And this transformation can be done by edit operations. We can insert or delete vertices or edges. And if we have labels, we can also relabel the vertices and the edges. A sequence of edit operations is then called an edit path. And each individual edit operation can have a cost assigned to them. And we then search for an edit path with minimal cost, and these costs are then the graph edit distance. If we have those two example graphs, we can find an edit path between them where we delete the edge in the middle, then relabel the vertex in the lower right, and then insert an edge on the right side. And if each edit operation had cost 1, this edit path had cost 3, and we couldn't find a cheaper edit path, so the graph edit distance between those two graphs is 3. The costs of the edit operations do not have to be uniform. For example, if we have graphs with attributed vertices, maybe coordinates, we could find a suitable distance measurement between them and use those as edit costs. Or we could have costs depending on a discrete label, so just a more complicated cost function. We assume that at least the edit costs are metric. The computation of the graph edit distance in general is an NP-hard problem, and the exact computation is not feasible for larger graphs. However, many approximations have been proposed. There has been done extensive research. Unfortunately, most of those approximations are not suitable for similarity search, but in recent years, a lot of research has been done on this also. All of those approaches can be mainly divided into two categories. One category compares overlapping substructures, and the other compares non-overlapping substructures. And in this table, there are just a few of those approaches. The first four compare overlapping substructures, and the next four compare non-overlapping substructures, so they partition the graphs. And then there are also approaches that are specifically for the verification step, which are the last two approaches in this table. All of those approaches, however, have the huge disadvantage that they only work with uniform edit costs, and most of them can also not process edge labels. Our contribution is a filter verification framework for graph similarity search that can process arbitrary metric edit costs, and we speed up our search through the use of a metric index and can support both range and k-nearest neighbor queries. And the KNN search is done through the usage of the optimal multi-step KNN search algorithm. I'm going to give a quick overview of our approach. First, an initial candidate set is generated through a lower bound combined with an index. We can filter out all graphs where the lower bound is already greater than the specified range because the exact distance can only be greater than the lower bound. Then subsequently tighter upper bounds are used to hopefully report a lot of candidates as results. If the upper bound is lower or equal to the specified range, we know that the exact distance is only smaller, so we can report those candidates as results directly. If we cannot filter out the candidates or report them as results, we'll use of lower and upper bounds. Then we have to verify the remaining candidates in the last step, where we decide finally if they're in the result set or not. We have two setups, the blue one and the yellow one. The blue one is for arbitrary metric edit costs, and the yellow one is for uniform edit costs. The yellow one is a little bit faster. I'm going to go over each step of the filter pipeline individually. Branch is an assignment-based lower bound, which means we compute an optimal assignment between the vertices of the graphs and derive a lower bound from that. For this, a cost matrix is needed, and this cost matrix is based on the cost of the individual edit operations, and the cost of this assignment is then used as the approximation, so the lower bound of the graph edit distance. For the runtime, of course, we have to solve an optimal assignment problem, which can be done in cubic runtime, so that's the second part of the runtime. And in order to compute the cost matrix, we have to solve an optimal assignment problem on the edges of each vertex pair, so that's the first part of the runtime. The branch lower bound is proven to be a metric if the edit costs are metric. So I'm going to give a quick example, and for simplicity reasons, we assume that the edit costs are uniformly 1 and that we don't have any edge labels. First, we extend the cost matrix with dummy vertices to allow for insertion and deletion of vertices, which is the grayed out area. Then each entry of the cost matrix corresponds to the cost for substituting the vertex label plus the minimum cost for substituting the edges. For that, we have to solve an optimal assignment problem on the edges. And to avoid overestimation, we halve the edge cost. We can find an optimal assignment. In this case, the cost of the optimal assignment is 2. So our lower bound is 2, and we have seen that this is a valid lower bound. If we have found a candidate set with this lower bound, we can also derive an upper bound from the assignment found by branch. Because we can derive an edit path, and an edit path, or the cost of an edit path, is always an upper bound for the graph edit distance. And we can derive an edit path from an assignment by basically just going through each vertex and its assignment and checking whether it has to be inserted, deleted, or relabeled, and adding costs accordingly. And then we go through each edge, look at both endpoints and their assignments, and again deciding whether this edge has to be inserted, deleted, or relabeled. If we have found an edit path, we can also use local search to improve this edit path, and the bound we get from this we call branch refined upper bound. We basically, to improve the edit path, we swap two assignments and check whether the resulting edit path is cheaper. So branch refined upper bound is always tighter than branch upper bound. For uniform edge edit costs, we have a faster variant of branch, which we call branch const, and it's a little bit faster because we don't have to solve the optimal assignment problem on the edges, but we can just use the multi-set intersection of the edge label sets, of the edge label multi-sets. For verification, we use BSSGED, which is fast, but unfortunately is only suitable for discrete labels and uniform edit costs, so we use this in our pipeline for the uniform edit costs. And for arbitrary edit costs, we used an integer linear programming formulation where we added an additional constraint which allows for early termination. We can also do KNearest neighbor search, but for this the filter pipeline is not that clearly separated. We use the optimal multi-step KNearest neighbor search algorithm, which minimizes the number of candidates that have to be verified And it basically works like this. We start with a range query with infinite range, and then we process each candidate in ascending order regarding their lower bound distance to the query object. And we immediately verify each candidate and use the information gained from the verification to decrease the search radius if possible. We also conducted several experiments with our framework. First, we looked at the selectivity of the different branch bounds. We compared different metric indices to each other, mainly the cover tree and the vantage point tree. And then we also compared to state-of-the-art approaches, but all of those require uniform edit costs, and our approach can also do arbitrary edit costs. So when we look at the selectivity of the different bounds, in red we have the initial candidates reported by the branch lower bound, and then we have the results reported by the subsequent steps of the filter pipeline. We can see that for larger thresholds, the branch lower bound gets increasingly loose, and also the branch upper bound doesn't report a large portion of the results. The branch refined upper bound, however, does a pretty good job at reporting a lot of the results. When we compare different index structures to each other and to using no index at all, of course, these index structures require preprocessing. The index has to be constructed. But in the filtering step, we get a huge speed up, and the cover tree, although it is a little bit slower in filtering in most data sets, it does a pretty good job in the latter data sets, and it is faster in preprocessing. So the cover tree might be a great choice for an index. Compared to state-of-the-art approaches, we can also compare the preprocessing time. We compare the filtering time and the total query time, which is the time needed for filtering plus the time needed for verification. And we can also look at the filter quality. We see that at least the cover tree is as fast in preprocessing as the other approaches. And although we're a little bit slower in filtering than, for example, GSIM, when we look at the total query time, we are the fastest. And this might be because if we look at the filter quality, the branch pipeline has a lot fewer results to verify. So because we have the tightest bound, we are the fastest. So in conclusion, we can say that we achieved a huge speed up through the use of a metric index. And we also can process large databases. Our approach also can be used with arbitrary cost functions as long as they are metric, and we can support both range and KNearest neighbor queries. For the future, it might be interesting to embed the branch lower bound into vectors, so we can use it with locality-sensitive hashing-based search. Because we have seen that the branch lower bound and the larger thresholds might not be tight enough, we would also like to develop a new lower bound that is tighter than branch, or which also has a good runtime and can be used with an index structure. Thanks for your attention.